For the last decade, enterprise digital transformation has focused on a single objective: instrumenting the physical world. We placed sensors on assembly lines, connected supply chains, and built digital twins to make operational environments fully observable. Frontier models and agentic AI have shifted the center of gravity. We are now augmenting the analysts, engineers, and planners who interpret data and execute knowledge work. This shift has exposed a critical category error in enterprise architecture. We are conflating the AI required to manage physical reality with the AI required to perform cognitive execution. To fix this, we must separate them. The first layer consists of smart systems, which optimize operational environments by capturing raw signals. The second layer consists of Deepwork agents, which govern cognitive tasks. Their purpose is transforming human intent into executable artifacts. The most effective enterprise architecture doesn't force a choice, it integrates them, positioning the cognitive layer directly above the physical layer. Deploying a large language model directly into a stream of raw industrial telemetry creates immediate friction. Without a cognitive layer, the system generates a high-volume flow of unstructured alerts, increasing cognitive load and leading to alarm fatigue. Let's isolate the first layer. A smart system is an AI-enabled cyber-physical loop. Its precise function is to improve the visibility, prediction, and optimization of a managed physical environment. The defining characteristic of this loop is that it is strictly state-centric. Its sole concern is measuring the current, abnormal, or predicted state of a physical system. This chart models the state-centric flow. Raw data leaves the physical substrate, passes through sensing layers, and becomes a digital twin. The system applies AI to predict future states and generate control actions, which are routed back into the physical environment, closing the loop. This structure clarifies why a basic dashboard is not a smart system. A dashboard merely visualizes a current state. A digital twin actually models system behavior, allowing operators to run simulations and evaluate interventions before executing them. Modern smart systems are advancing past predictive alerts and into physical AI. This requires control policies trained and stress-tested in virtual simulations before touching physical operations. Because these systems act directly on the physical world, a wrong output can cause immediate damage. Therefore, primary design constraints are strict safety envelopes, fail-safe modes, and robust OT cybersecurity. The ultimate output of a smart system is never a cognitive work product. It produces operational intelligence, structured signals, risk forecasts, and state estimates that describe reality. The second layer requires a completely different architecture. A Deepwork agent is a governed, domain-specialized AI workmate. It exists to transform human intent into decision-grade artifacts. This is an intentional step away from standard chatbots. Conversational memory and open-ended text generation are too weak and unstructured to handle rigorous, auditable enterprise tasks. Instead of monitoring physical state, the Deepwork agent operates on an intent-centric loop. This chart outlines the intent-centric model. A human principal delegates an objective, formalized into a task contract. Guided by this contract, the runtime assembles context, invokes approved tools, and cycles through strict reasoning loops. This execution relies on a competent substrate. The agent accesses versioned knowledge bases, skills, and playbooks. Before completion, the runtime verifies its logic against enterprise policy, delivering a structured artifact back to the principal. Crucially, this artifact is fully interrogable. The principal can audit the specific reasoning traces and verify the source data before approving consequential decisions. Deepwork agents do not manage supply chains, and they do not optimize physical plants. They optimize the human worker's capacity to process complex evidence and produce executable work. To understand how these systems interact, we compare their governing rules. First, their ontologies are separate. A smart system processes assets and sensors. A Deepwork agent processes tasks and evidence. Second, they have different boundaries. Smart systems are restricted by hard engineering safety envelopes to prevent physical disruption. Deepwork agents are restricted by task contracts to prevent hallucination and tool misuse. Finally, we measure their success differently. Smart systems are evaluated on uptime and process economics. Deepwork agents are evaluated on artifact quality and decision impact. If you evaluate a Deepwork agent based on token generation speed or the volume of chat interactions, you are measuring the wrong variables. The only metric that matters is the accuracy and utility of the completed, evidence-bound work product. A smart system cannot be measured as if it were a knowledge worker, and a Deepwork agent cannot be managed like an industrial machine. When we stack these two isolated loops together, we create the Integrated Enterprise Intelligence Stack. To see how this architecture functions in practice, consider a specific industrial scenario, optimizing the maintenance strategy for a critical compressor train. The process begins at the foundational layer. The physical asset generates raw telemetry, which feeds upward into the smart system. The system compares it against the digital twin, simulates failure probability, and synthesizes a distinct block of operational intelligence. At the critical handoff, a human principal reviews this intelligence and delegates a formal intent to a Deepwork agent. The agent begins its cognitive work, querying historical records and calculating exact trade-offs between risk, repair costs, and downtime. Following its reasoning loops, the agent generates a reviewable maintenance strategy decision packet, listing approval pathways. The human principal interrogates the logic, verifies the source data, and approves the plan. The intervention is executed, resulting in a measurable enterprise outcome. The smart system generated the physical visibility, but the Deepwork agent converted that visibility into execution readiness. Together, they successfully closed the enterprise intelligence loop. We can now identify the central hazard of modern AI deployments. Adding more smart sensors and predictive alerts does not automatically make your work smarter. Without a cognitive layer to process them, those alerts simply multiply the cognitive load. Integrating these systems requires a strict governance principle. Do not rely on a model's declared intent when you need hard, enforceable controls. Governance must be built directly into the infrastructure. For smart systems, this means strictly enforced OT cybersecurity and physical safety boundaries. For Deepwork agents, it requires mandatory role-based access controls and restrictive tool harnesses that limit what the agent can actually execute. The objective of deploying these technologies is not to build an autonomous void where humans are entirely removed from the operation. The strategic destination is a carefully layered enterprise. Smart systems optimize operational reality, Deepwork agents augment cognitive execution, and human principles retain the ultimate authority, judgment, and accountability for every consequential decision.